this lecture, we're going to be covering Units 9 and 10 in our Math Applications for Healthcare textbook. And we are going to look at pre-algebra basics in Unit 9. And then in Unit 10, we're going to take a look at reading drug labels, medicine cups, syringes, and intravenous fluid administration bags. All right, so some uses for algebra. I have to laugh because, it's always been my experience with algebra is that how am I ever going to use this in my everyday life? So I'm going to give a shot at connecting algebra to our daily lives as well as our professional lives. So algebra is the study, understanding, and use of symbolic reasoning, mathematical properties, processes, and calculations to problem solve for a variety of unknown situations. This unit is going to lay the foundation for algebraic concepts. And in healthcare, the use of algebra is seen in the use of formulas to solve problems. One such formula might be the conversion between temperature systems. If you don't follow the order of operations, for example, when you're calculating the temperature formula, as we talked about, I mentioned order of operations a couple times, you're not going to get to the correct solution. In addition, dimensional analysis is an algebraic formula used to convert measurement systems. And we've done this before, right? We've said the unknown. Maybe we've used a question mark. I have talked about using X in place of the unknown. And this is basically the same thing. So we've already been working with unknowns. We just haven't really slapped on the label of algebra, right? So typically, some of these math outcomes won't be used in everyday healthcare settings except in laboratories, math courses, and statistics. However, the more we hone our craft at doing math, the more we exercise that analytical and critical thinking area or areas of our brains. And critical thinking and analysis are two extremely important components for us in our role as surge techs. All right, so we talked about integers. Dig way back into the beginning, chapters 1. We talked about integers, and we use those, right, to solve everyday math problems. And integers consist of positive whole numbers like 1, 2, 3, 4, 5, 6, all the way to a million, and their negative counterparts, -1, -2, -3, -a million, and everything in between. And then there's the zero. The zero isn't positive and it isn't negative. It is Switzerland, right? It is neutral. It doesn't pick a side, positive or negative, right? It's an independent. So integers are used to form this countable infinite set, right? And you can see this number line here. We've used it before when we were talking about relationships between negatives and positives and how the zero fits into that. So the number line, again, is a line that is labeled with integers in increasing order from left, right? Left is the negative numbers. 0 is in the middle, essentially. And then the right side of the number line has all the positive numbers. So remember that any integer on the right is always going to be greater than its partner, its friend to the left, right? The right numbers are always increasing, okay? So let's maybe apply this to the healthcare setting. So what if we have a hospital, let's say it's an OR department, and they add 3 additional surge techs to their staff? That would be a +3 of staff, right? What if 3 surgical techs quit and they go somewhere else? That would be a loss of 3 surge techs, and we would represent that by -3. So in this example, we can understand that terms that indicate negative integers uh, um, are represented by a negative sign, right? And then those that represent positives or gains are represented by a positive sign. Or if it's positive or if there's a whole number and there's no sign, we're going to assume that it is positive. All right. Now the negative and positive, if you've been around accounting or bookkeeping, you'll know that a negative number indicates a loss, while a positive number indicates a gain. I see so many negative numbers in my bank account, right? I get every 2 weeks, I get a positive gain. I get a gain in my bank account, right? And then there's all of these deductions, and those are represented by a negative, or sometimes they're shown in red, right? So negatives and positives can also represent losses and gains when we're talking about money or something like that. All right, so the absolute value. An absolute value of an integer is going to indicate its distance from 0 on the number line. And so this is going to take away the sign. All right, the absolute value of a number such as 3 is shown as 3, and you can see how it is confined between these two vertical lines, right? So if we say, what is the absolute value of a -3, right? That would be 3, okay? The absolute value is never negative, all right? The absolute value only asks how far, right? How far away it is from 0 on the number line. So that means that a +3 would be 3 away, and a -3 would be 3 away. All right. So integer operations. Now, the use of basic math functions like addition, subtraction, multiplication, and division are used to solve math problems, right? We know that. They involve like signs and unlike signs. So let's talk about what that means. All right, so here we are adding 2 numbers, and they happen to be positive numbers. All right, so remember that the absolute value is the distance from 0 on the number line. So to add integers having the same sign, we're going to add their absolute values and then use the same sign as the number that we are adding. Adding positive integers is just like adding whole numbers. Like when we say 2 plus 7, right? We're to assume, because there is no sign, that they are positive, all right? So the numbers move right on the number line, right? When we're talking about a +2 plus a +7. So what if we are adding 2 negative numbers? Well, the same thing is true. They have the same sign. That's our clue. All right. So when they have the same sign, we simply add the numbers and then place the sign in front of the number. So a negative 4 plus a negative 3 would give us a negative 7. So what if we're adding integers with unlike signs? So the first thing to remember is that the absolute value is the distance from 0 on the number line. So to add integers having different signs, we're going to subtract their absolute values and then use the sign of the larger number. The number line is very helpful when adding numbers with different signs. So you can see the number line shows the sum of negative 5 and positive 8. So note that the positive integer 8 is larger than negative 5. So the answer is going to be 3 or positive 3. Okay, so remember, when we are adding integers with unlike signs, we're going to subtract the smaller number from the larger number and retain the sign of the larger number. Okay, so when we are subtracting integers, the first step is going to be to change the math function sign, that negative sign that you see in the middle in the example here between positive 5 and negative 9. We're going to change that to a positive. The second step in subtracting integers is that we're going to change the number sign to its opposite. So I'm not sure if the book is confusing at all to you or if it was just the way that I was taught to do this. But for me, the way I think of this, if we look at the example, positive 5 minus a minus 9, do you see those parentheses around the 9? This is basically like multiplying the negative sign by the negative sign. So the two negative signs being multiplied together changes it to a plus. All right? So if it helps you to think of it as that way, like when you see two negatives together, they multiply and that changes the sign. All right, so whichever way it helps you to think about it, of changing the operation sign and then changing the number sign, you can think of it that way. If it helps you to think of it as we're multiplying the negatives together, and when you multiply a negative and a negative, you get a positive, you can think of it as that as well. All right, so that's going to be, the next step is going to change the number sign to its opposite. So this is going to give us a positive 5 plus a positive 9, or we're back to 5 plus 9, right? And that gives us a positive 14. Okay, so now let's talk about multiplication of integers. Now, multiplication of integers can be presented in a variety of ways. In whole numbers, we saw multiplication problems that looked like this first one here, 2 times 4 equals 8, right? In an algebraic format, you might see it written the second way, where the 2 and the 4 are in parentheses. That means we multiply them together. Or you might see the multiplication sign represented by a period or a dot in between, right? The two. And both of those tell us to multiply. So these three ways are all saying the same thing. Please multiply 2 and 4 together to get your answer of 8, all right? The reason that we typically don't use the X multiplication sign in algebra is because X is usually the variable that we use to represent the thing that we don't No. Sometimes you might see it as n, but for the most part, if there's only one variable in an equation, we're probably going to default to using the x for that, and so we avoid using the traditional multiplication symbol, okay? Now, when we're multiplying integers, the multiplication operation is going to be the same regardless of if it's a positive number or a negative number. The thing that we have to think about when we're multiplying integers is what sign we are going to add to our product, right? When we multiply the two numbers together, or multiple numbers together for that matter. So to determine the sign of the product, if we are multiplying a positive and a positive, that's just like normal old multiplication. That's going to give us a positive whole number. So we can put a plus, or we can just put the number, and then it would be assumed that it's positive. Now, if we're multiplying a negative number times a negative number, that's going to give us a positive answer. Here it goes back to when I was saying a minus multiplied by a minus gives us a positive. All right, so in the example here, a -6 times a -7 is going to give us 42, or a positive 42. Lastly, if we're multiplying a negative times a positive, this is the only situation where we're going to get a negative number, right? If we're multiplying opposite signs. So a -5 times a +6 is going to give us a -30. Another difference in algebra is when we're dividing integers. Now, typically when we're dividing whole numbers, we use the division sign that you see here. In the algebraic format, we're either going to use a slash or a fraction bar to indicate a division sign. So the rules to determine the sign of answer for a quotient are as follows. If we are dividing a positive by a positive, that is going to give us a positive. If we're dividing a negative by a negative, again, we get a positive. It is only when we are dividing a negative and a positive number, or a positive and a negative number, either way, we are going to get a negative answer. So same as multiplication, the only place where we're going to have a negative quotient is if we have a positive and a negative number in the division problem. So let's talk a little bit about something called exponential notation. And I've seen a couple of you using this on your homework, and that's awesome. So exponential notation is a useful means for writing a product of many factors. The base is the number that is being multiplied, and then the little superscript number that you see kind of to the top and the right of the number is called the exponent. The exponent. So if we have a number like 3 to the 5th, sometimes we call this 3 to the 5th power, right? That means it's going to be 3 multiplied by to itself, multiplied by itself 5 times. So 3 times 3 times 3 times 3 times 3. That would be 3 to the 5th. So this example has 3 forms here, and they all mean the same thing. All right, the first form is the exponential form, or exponential notation of 3 to the 5th power. The factor form, which we've done factoring in the past, so this should make sense to us, is the repeated multiplication of 3 times 3 times 3 times 3 times 3, right? Or 3 with the parentheses, or 3 with the dots between. All of those are the same. And then the last is the standard form, where we actually worked it out and we multiplied 3 times 3 times 3 times 3 times 3, right? Where I see sometimes a mistake occurring is when we do 3 times 5. All right, this is not 3 times 5. This is 3 times itself 5 times. All right. So some rules. All right. There's always rules, right? The first rule is any number raised to the first power is always equal to itself. All right. That little one is always imaginarily sitting there anytime we have a whole number. So 7 to the 1 power is 7, right? Or any number raised to the first power would be itself. Let's look at the second rule. The second rule is if a number is raised to the second power, we say that it is squared, right? That's algebra speak, exponent speak, all right? So here the example, 5 to the second power, we would say 5 squared, all right? And then the next rule is if any number is raised to the third power, we say that it is cubed. So here we have 4 to the third power, and we would say that as 4 cubed. All right, let's look at our next rule. The next rule is that any number that is raised to the power of 0 equals 1. All right? Any number raised to the 0 power equals 1, except 0 to the 0 power, which equals 0. That one's a little bit weird. But 9 to the 0, a million to the 0, 1 to the 0, 15 to the 0, all of those are going to equal 1. However, if we have 0 to the 0, that is 0. Anything times 0 is 0. If we have 0 to the millionth power, it is still 0. All right, so handling 0 is a little bit different, but that is how we do it, okay? All right, let's look at this next sign that you see here, this weird like check mark with an extended line. Maybe you've seen it before. It's called a square root. And I remember when I was in my junior college and we had this math instructor. It was for intermediate algebra. It was in my freshman year, and he had some sort of speech impediment, and so we were learning about square roots, but he called them square woods. Square woods. So it took us a minute to figure out what square woods were. Anyways, here it is, the square root sign. Looks like a check mark in a line. And to find the square root of any number, the way that we're going to do it is find the factor that when multiplied by itself one time, it equals the number inside the square root. So let's look at an example. The example we have here is we want to take the square root of 100. And what times itself equals 100, right? We're talking about the square here. Remember when we said anything to the second power is squared? Now here we're taking the root of that, right? The root would be that base number, right? And so when we multiply 10 times 10, we know we get 100. So the square root of 100 would be 10. All right. Some more examples are listed here. The square root of 16. What times itself equals 16? Well, that would be 4. The next example, 36. We multiply 6 times 6 to get 36. And then the square root of 81, we multiply 9 times 9 to get 81. So those would be the square roots of those numbers. Now let's talk a little bit more about order of operations. You might have heard this a few times by now. So now we're going to get into some of the details regarding orders of operations. And then I have a little, I guess you would call it acronymic sentence or something like that to help us remember the order of operations. Kind of like how we had one for the order of the metrics system for conversions. All right, so when we perform operations, the reason we're doing this is so that there is a standard order of operations for calculating a problem, right? So when we follow the order of operations, this allows for a correct answer, only one correct answer for each problem. So again, let's look at some rules. There are 3 of them, all right? The first one is we want to perform any calculations involving parentheses, fraction bars, exponents, and square roots first. Okay, that's the first thing we want to tackle. So what's the second thing we want to tackle? The second thing is that we want to perform all multiplication and division, and we're going to do this working left to right. So just like you would read a sentence along the page, just like you're reading the words on this slide, you're reading from left to right, that's the way that we're always going to perform our multiplication and division. Now here's a look at the third rule. The third rule is that we are going to save the best for last, and that is our addition and subtraction. Again, working from left to right to perform the operations. So you might have heard of this before. I did not make this up. It has been around for a long time. But here's a way to help us remember the order of operations. And that is the acronymic sentence, please excuse my dear Aunt Sally. Now when we just take the first letters of that sentence, we get PEMDAS. PEMDAS. So what I do to help me stay on the straight and narrow when I'm doing these problems that require multiple operations is I'll just go ahead and write PEMDAS right next to the problem that I'm working. And then I'll just slash them out as I go. I'll look for any parentheses, exponents, so on and so forth, fraction bars, and if there's none there, I'll just simply put a slash through the P. Right? Or if there is, I'll perform them and I'll slash it out. And then next, I'll look for any exponents or roots. Same thing. If there is none, I'll slash out the E or cross it out. If there are some, then I'll work them and then rewrite my problem and cross out the E. And so then I'll just work this way through each operation. Right, so following the exponents and roots like we talked about is multiplication and then division working from left to right and then followed by addition and subtraction. So PEMDAS is going to really help us when we're working these problems. All right, so here's an example of an order of operations. We're going to follow PEMDAS to get our correct answer. And so let's look at this. We have 5 plus 7 times 8. Now, let's ask ourselves, are there any parentheses? Or are there any exponents? No, there's not any of those, right? So we can X those out. What about multiplication? Is there multiplication? Aha, yes, there is, right? So we're going to work left to right and we're going to multiply 7 times 8. And then when I do that, I rewrite my problem again. So you can see how they've done this here in step 2, 56, and then bring down what I have left, right? Which is to add 5. We're going to add 5 to that. All right, so we performed our multiplication. There isn't any division. Is there addition? Yes, that's the last thing that we have. And so we're going to go ahead and add that to our 56, and that gives us 61. Now, there's also an example of what not to do, right? And that's just to simply go 5 plus 7 times 8, right? If we do that and we do 5 plus 7, we get 12, and then we multiply our 8, we get 96, which isn't the correct answer. All right, so we always want to follow PEMDAS when we are performing these operations. All right, moving into alphabet soup meets math, right? So when we have some sort of letter that is representing something we don't know, an unknown number, we call that a variable, right? And a variable can be used in addition, subtraction, multiplication, and division. Variables do not discriminate. They like to be involved in all types of math. Something else you might see is what is called a coefficient, right? Some variables have a friend that comes along with them, right? Maybe it's an imaginary friend, I don't know. And that is called a coefficient, right? So in the example that you see here, we have a negative 8x. So the negative 8 part is the coefficient and the x is the unknown, right? This is the same as saying negative x times or negative 8 times x, right? That's the same thing. So an expression, quote unquote, is a mathematical statement that may use numbers and or variables. An algebraic expression is an expression that contains one or more variables. So you can see a couple examples here of expressions in algebra. The first one is 9 plus z. The next is x times y. The one after that is 9 times 3 minus x. And then we have a 20 plus 9 minus x. And 9 minus x is set in parentheses there. An expression is also used to build a mathematical statement from words. And these are, most of the students I have, word problems are their favorite. No, I'm just kidding. I can remember in my junior college and my undergrad and my master's as well, I studied accounting because I was a business major. And those word problems always seem to be the trickiest, right? There's keywords that we can look for. And so let's look at an example here. This first example says an LPN spends $240 on books. That's something that we know. It's a known amount they are telling us. The second part says dental assistants spend Y on books, right? That's an unknown amount. Y is a variable that's representing the cost of books. We don't know it. It's unknown. So if we were to write an expression for total cost, right, their combined cost spent on books, then we would write something like this: $240 which is what we were told LPN spend on books, plus y, which is what we don't know that the cost that dental assistants spent on books. All right, we can't solve this. We're not focusing on solving so much here as just getting a better idea of how to write an expression, right, from a word problem. So some common algebraic expressions are as follows. We're going to go over a few of them. The first one is some number n increased by 2.7 inches, I guess is what that's supposed to be. Oh no, it's just quotation marks, never mind. 2.7. Okay, so when we see the word increased, that should clue us in that we're going to add. And so we can express this as n plus 2.7. So let's take a look at the next one. The next one is 9 less than some number x. All right, so here, don't let this trip you up, right? Because it's 9 less than something. All right, so we're going to be subtracting 9 from x, from some number. So when you see the word less, that should clue you in to you're going to have to subtract something from something. Well, the next one is the sum of two numbers a and b. Again, sum, that's going to tell us to add, right? And here we're adding a plus b. So let's look at some more common algebraic expressions. Some number q multiplied by 5. When you see the word multiplied, that's going to tell us to multiply, right? And so we can just write the 5 and the q just all cozy next to each other. Then that's going to represent multiplication. The next one is product of x and negative 9. Again, product signifies multiplication. So again, we can cozy those two up and we would express this as minus 9x. Another one might be 4 times the sum of three numbers, x, y, z. All right, so we're going to, we have two words in here, right? To tell us we're going to perform two operations, sum and times. Times meaning multiplied. So the 4 is going to be multiplied by the sum of three numbers. All right, so we would use parentheses to group the numbers we're going to add together, which is x, y, and z. And then we will set the 4 right outside of the parentheses to signify that once we add all those numbers, we're going to multiply them by 4. So what about evaluating expressions? Okay, still, again, we're not solving, but evaluating. Algebraic expressions are not solved, as in computation, like 5 plus 4, but they are evaluated. All right, the value of the variable is often given and it is used to replace the variable in the expression. So let's look at an example. What does all this mean? So here we're evaluating 5y plus 12 when y equals 11. Okay, so just told us what y is, so we can plug in 11 for y. And that is going to give us 5 times 11 plus 12, right? 5 times 11 plus 12. And when we use our order of operations, our PEMDAS, we don't have any parentheses or exponents in this particular equation or expression. The next thing on the list is multiplication, right? So we're going to do that first. We're going to multiply 5 times 11, that gives us 55. And then there isn't any division, but there is addition, right? That's what comes next in our order of operations, and so we'll perform the addition and add that 12 to our 55, and that gives us 67. So the algebraic expression evaluated with y equals 11 is 67. All right, moving right along, this is a very, very super helpful chart here. So keep this handy when you're performing when you're evaluating expressions or writing expressions, and that will help you to identify, do I put an equal sign, a plus, a minus, a multiplication sign, or division sign. So reading word problems requires attention to detail, and this is just another area that directly relates to the role of the surgical technologist. Start to hone your eye, and math can definitely help us do that, right? Draw us in to getting better at paying attention to details. So sometimes there can be confusion over some expressions. And here's some examples. 5 more than x, right? 5 more than x. That means we're adding, right? We're adding 5 to x. If we have something like 5 is more than x, then we're saying 5 is greater than. 5 is greater than x. Here we have an equation or an inequality. Another example of possible confusion is 4 less than z, right? That's going to be z minus 4. Or 4 minus z is going to be 4 minus z. See how they're backwards? So if you have a less than, right, you're going to be taking that away. Or this, the second one is just, you literally write it out how it says. 4 and then a minus sign and then a z. And then lastly, 4 is less than z is kind of similar to our 5 is more than x. So this would be written as an inequality of 4 with the less than sign and the z to follow. So how would you write an expression to represent that you got 12 points higher on this anatomy test than on the last one? The way that we would write this is 12 points higher on this test than on the last test. We're going to let x represent the score on the last test, and we are going to add 12 to that. Right? So the expression would be x plus 12. To solve an equation, we need to get the variable by itself on one side of the equal sign. Now we've kind of been doing this with solving our proportions, solving for our unknowns, right? And so this is going to be similar in a lot of aspects to that. When we need to get x by itself, we do something called using inverse operations. So inverse means the opposite. Remember, addition and subtraction are opposites, and multiplication and division are opposites. Okay, so when we do that, we have to do it on both sides of the equation. Okay, we're going to perform the same operation. Let's look at an example. So here we have the example of x plus 1.5 equals negative 5.2. All right, so we need to get x all by itself. X is our variable, right? So we need to get rid of that 1.5, right? The easiest step would be to get rid of it so that x will be by itself. So how do we do that? Well, first we have to look at what's happening between the x and the 1.5. Here, they're being added. So now that we know that the operation is addition, we can identify the opposite operation, which is subtraction. So we are going to subtract 1.5, and that gives us nothing on that side. And we're going to do the same to the other side, right? We're going to subtract 1.5. We have to do it on both sides, right, to keep things equal on both sides of the equation. And so when we subtract 1.5 from negative 5.2, right, that's like adding them together, basically, we get a negative 6.7. X equals negative 6.7. So an algebraic equation is an equation that contains one or more variables. We said that before. So there also be algebraic expressions on both sides of the equation. So an equation is essentially a mathematical sentence with an equal sign that illustrates that the two expressions represent the same number. They're equal on each side, okay? So this is helpful information for us to know when we get an answer and we're not sure if it's right or not. We can plug it in for our variable and see if we get the same number on each side of the equation. If we do, then bingo, we know we have the right answer. If we didn't, then we know we have to go back to the drawing board, right? So when we have word problems, right, we have to be able to translate that word sentence or other information into an equation. So let's look at this problem, and then we will work through how we translate it into an expression, an algebraic expression. Okay, so here's the problem. If a patient's current temperature decreases by 2 degrees, it will be 99.4 degrees. So we want to know what is the patient's current temperature. Okay, so let's look at how we decipher that. All right, so here we see a portion of that problem. Temp decreased by 2 degrees is 99.4 degrees, right? So we can use a T to represent temperature, and we are going to decrease the temperature by 2 degrees, right? So that would be the current temperature that we don't know minus 2, and then is represents the equal sign 99.4. It's telling us it's equal to 99.4. So how do we solve this? Well, remember we said we have to get the variable all by its lonesome. So let's look at the relationship between t and 2. Here the relationship is subtraction. So what's the opposite operation of subtraction? If you said addition, congratulations, that's awesome. You are absolutely right. So we are going to add 2 to both sides of the equation. Remember, we have to do what we do on one side of the equation of the equal sign, we have to do on the other side of the equal sign. Always, always, always. All right, so we're gonna add 2 to both sides, and that gives us an answer of t equals 101.4 degrees. So that concludes our discussion of Unit 9 and all the fun that solving algebraic equations entails. And now we're going to move on to discussing Unit 10. And in Unit 10, like I mentioned, we're going to be looking at the different parts of the drug label, different parts of the syringes and needles, and working on being identifying all of those different components. And then we're also going to talk about labeling syringes and medicine cups for proper dosaging, which is something we do as a surgical tech every day in the field. We're also going to practice reading intravenous fluid administration bags and use the drug labels to find key dosing information. So here we go. Math doesn't get more applicable to the field of surg tech than this unit here. Okay, so let's go over some concepts first so that we just understand the terms that I'm going to be using in the rest of this lecture. So when we talk about the generic name of a drug, this indicates the chemical name of the drug and includes any drug marked under its chemical name without advertising. All right, the generic brand. All right, we have Kleenex, and then we have Kroger brand or Walmart brand or something of that sort. All right. Now, the generic name is usually what is going to be displayed on the label. And so that's typically what we are going to be writing is the generic name when we make our labels. The trade name is the brand name. So again, it's the Kleenex name. It's the brand name. And you might see a trademark symbol indicating that it is indeed the trade name. Now, the manufacturer is going to indicate who makes it, right? And then there's something called the National Drug Code Number or NDC number, and this identifies the manufacturer, the medication, and the container size. They all have specific numbers. The lot number or control number is placed on the label prior to shipping to identify the lot. Right? So there was a group of them that were produced at the same time, and those are marked accordingly. This is super important when, let's say, I can speak to a personal experience about this. In the operating room, I was doing a knee scope, and the tubing that we use for continuous irrigation during a knee scope was recalled. A certain lot number was recalled, and that happened to be all of the tubings that we had in our supply. So that was created a situation. And so the situation, is that if something is found to be malfunctioning as far as like an implant or a product or a drug is contaminated or something like that, then this lot number will help us identify that group. All right. The drug form. There's several drug forms, and we're going to talk about them in detail when you are in your pharmacology class. But some forms may include creams, capsules, caplets, drops, droplets, suppositories, syrups. It could be powders, it could be ointment. There's a whole variety of them, all right? The dosage strength is going to provide the strength per dose in a tablet, a milliliter, or a syrup, and we've been talking about that. The usual adult dose might also be indicated on the label. The total amount in the vial, packet, or box is also going to be somewhere on the label, and that is going to tell us the total number of items that are in the container. There could also be a prescription warning that indicates that the medication is a prescription drug. And lastly, an expiration date, which is something that we will always be checking when we're working with medications in the operating room. Okay, so that's our overview. Now, digging in a little bit further, let's take a look at a label. So reading medication labels, like I said before, is something that we're going to be doing every day as surg techs. So take a second and look at this label and see what you see. right? Check out the anatomy of the label. Go ahead and pause the video lecture if you need to. And you can see that they've already kind of labeled things, but just take a minute or two to check it out and locate the information on this label. So some of the things that you might have seen was the generic name, right? The generic name is morphine sulfate, and the manufacturer is PL Pharmaceuticals. The national drug code and the lot number is not shown on the label, but the drug form indicates that it's an injection, and the dosage strength is 10 milligrams per ml. Does that look familiar? The usual dose isn't specifically given. If you remember on the label, it just says see package insert. And then the total amount, it says that there's 1 milliliter vial. That's a 1 milliliter vial. Some other information that was on there is that the prescription warning indicates that it is prescription only. RX is an abbreviation for prescription. And then the expiration date is not shown on this particular label. Now, in the operating room, if there's not an expiration date, we wouldn't be using it. I have never had a situation, not to say that you won't, but I've never had a situation where medication we were using on the operating room field did not have an expiration date. All right, but things are kind of shifting out there where we're going to something called event-related sterility, and so sometimes that's the case if there is not an expiration date. So a little bit about controlled substances. The Controlled Substances Act, or CSA, entails that drugs and other substances are divided into classes or schedules. And there's 5 of those, and it's based on a few things. One of the things is it currently accepted for medical use in the United States? That's one thing they consider. Another thing is its potential for abuse. And then the last thing is its likelihood of causing dependence. So classification lists are published annually. And let's look on the next slide what those are. So here you can see the breakdown of the schedule or class and the reason for the classification. So number 1 is going to be I don't know if you want to say the most risky class of drugs, where class 5 is going to be the least amount of risk associated with it, if you will. Class 1, they do not have any accepted medical use. They have a high potential for abuse and lack acceptable safe use for medication practices. This could be something like methamphetamines. Class 2 has high potential for abuse and may lead to severe psychological and physical dependence. Class 3 has a potential for abuse and may lead to moderate or low physical dependency and high psychological dependence. Class 4 has a low potential for abuse in comparison to those in Class 3. And then the Class 5 has a pretty low potential for abuse in comparison to Class 4, may consist primarily of preparations containing limited quantities of certain narcotics. So having a basic understanding of these schedules helps us in healthcare to have an understanding about the safety and the safe use of medications, and this is especially important for safeguarding opioid medications. And there will be times when you're using them on the field. We actually use liquid cocaine for some cases where we're working inside the nose. And then you may also be drawing up morphine on your field as well. So medicine cups is the first thing that we're going to talk about, and they're used to dispense liquid medications such as cough syrup or Maalox. In the operating room, we will typically receive medications like local anesthetics or a contrast dye, something like that. So to measure accurately, first we're going to get the solution into the medicine cup, and then we want to make sure that the medicine cup is on a level surface. And for us, we'll typically have it on our back table so that we can get an accurate reading of how much is in the cup. So let's look at an example here. Let's say that the preference card calls for 20 milliliters of some sort of medication, and the nurse is going to pour that into our cup, let's say, as an example for the surge tech. So anyways, you can see here that the amount of fluid in this cup is in fact 20 mLs. Now on these medicine cups, we see teaspoons and tablespoons on the left side and mLs on the right. Sometimes we might encounter this in the operating room as well. What I see more commonly is ounces on one side and milliliters on the other side. So let's practice reading a medicine cup. Well, the problem is the medical assistants were asked to dispense 7.5 milliliters of a liquid medication. So this is asking, where would we mark the medicine cup to indicate this dosage? And because there's not a lot of lineage here, right, we can kind of guesstimate between 5 and 10, and then we're going to go a little bit north of that. All right. So syringes come in a variety of sizes, and medications that we put into syringes are typically referred to as parenteral medications, and these types of medications mean that they get injected, right? And so here are some different types of syringes here that you might see in the operating room. Some common ones: 12 mLs, 10 mLs, 5 mLs, 3 mLs, and then we have our TB syringes. You might also see syringes that are 20 mLs, 30 mLs, and 60 mLs as well. All right, and on these, you have to, if you look at the biggest syringe, you can see that every mark indicates 1, whereas there are some where each mark is going to indicate 2. So it just depends on what syringe, how it's actually measured, or what the lines mean as far as measurements go. So here are the 3 components of a syringe. So the 3 components are the barrel, which is the actual syringe part that the fluid is held in. The plunger, which is the inside part. It's that image on the bottom of the screen that you're seeing, and then the barrel is the middle picture. The plunger fits inside the barrel, and it's attached to a rubber stopper, and the plunger helps to draw in or force out liquid or air into or out of the syringe. And then there's the tip of the syringe, and the tip of the syringe holds the needle. There are a couple different types of tips. There's one called the slip tip, which the needle just pushes onto and you can pull it off from. Or there is what is represented in this image called a luer lock syringe. And a luer lock syringe is one where you have to actually twist or screw in the hypodermic needle. So the parts of a hypodermic needle include the hub, the shaft, and the bevel. The bevel is what's going to cause the opening in the skin when it gets inserted into the patient. The shaft is the length of the needle, right? And then the hub is the actual part that's going to attach to the syringe. So, syringes come sterilely, right? And like I said before, they're going to be labeled typically in mLs, but different syringes are going to be going to have, the lines are going to have different units of measure. So as we work in the operating room lab, you'll get a better idea of which syringes, have which markings and how to read those. And sometimes you might see it labeled as CCs, but we're really moving away from CCs and typically now only use mLs. So in here, you can look at this slide and just get an idea of how much is in each of these syringes. The top one has 2.2 mLs, and you're going to read it at the very top of the plunger, right? Where the fluid touches the black part, that's where you're going to read it from. All right, because we're reading either how much was used or how much is left. All right, so we want to read it where the stuff is touching the black part of the plunger. The second one is a TB syringe in the middle there, and a TB syringe is only 1 ml. Right, so here we have 0.5 mLs in there. And then the bottom one is marked at 5.8 mLs. All right, so let's look at this IV bag. This is a common thing that you'll see in the operating room, and sometimes we might be reading like how much is in the Foley bag or how much irrigation was left if we're using IV irrigation or so on and so forth. And so it's important to know how to read these. And so this you see is marked at 4, 3, 2, 100, and then 0 mLs. And so if we're wanting to know how much is remaining, we're going to look at the total, right, which is 500 mLs, and then we're going to subtract what was infused, right? And this bag indicates that 200 mLs was infused, and so then that's just a simple subtraction problem there. Well, let's look at a couple other ones. The one on the left, they're wanting to know the volume infused there, right? And so the total volume is 10, and then if the fluid was at the 0, that would mean 0 was infused. If it's at the 1, that would mean 1 was infused, and if it's at the 2, 2 was infused, and so on and so forth, all the way down to 9, and then being empty would be a total of 10, right? And then if we look on the other side, it is at the level of the 9, and so the volume infused is 9. 10 minus 1 equals 9. So this concludes our lectures on Units 9 and 10, Algebra, and reading drug labels, med cups, syringes, and IV infusion bags. I hope this was helpful for you, and I appreciate you taking the time out to listen to this lecture, and I look forward to answering any questions that you might have in class. Thank you.